The goal of this video is to just give you a high-level understanding of the vocabulary of glaciers. What is a glacier? What are the words we use to describe different components of a glacier's anatomy? So to do that, we are just going to look at kind of a theoretical glacier system. This is a beautiful photo of a glacier from above. We can start to learn some of the terms we use to describe this system. In general, I like to think of a glacier as being defined by three qualities. The first is that it's a perennial body of ice. It sticks around for more than 1 year. Critically, it flows under its own weight. So subject to the force of gravity, that ice is actually actively deforming, and it's carrying with it mass from high elevation, typically to low elevation. And third, glaciers typically span a range of climate regimes. And we'll get into why that must be the case in a second. But what you'll find is that glaciers typically either span from high elevation down to low elevation, or they span from very high latitude at the poles down to relatively low latitude. So you can think about this image on the left as a cross-section of a glacier. And we can divide that glacier into two discrete areas. The first, which is up here, we might call the accumulation zone. This is where snow survives the summer high temperatures. So when snow falls, on average, more snow falls in the accumulation zone than melts over the warm season. And so year over year, there's a net addition of mass in the accumulation zone. It's where, on average, snow accumulates. In the warm regions of the glacier system, either at low latitude or low elevation, we have what we might call the ablation zone. Ablation is kind of a catch-all term we use to describe all of the processes that remove ice from a glacier system. So it could be melt at the surface from warm air, it could be sublimation, the direct conversion of ice in the solid phase to H2O in the vapor phase. It could be calving of icebergs into the ocean. It could be melt from ocean water. There are all kinds of processes that drive ablation. But in this downstream end of the glacier system, on average, more ice is lost than is added by snowfall. It doesn't mean that there isn't any snowfall over the course of the year in the ablation zone. The critical thing is just that more melts or is lost by ablative processes than is added by accumulation. The boundary between the accumulation zone and the ablation zone we call the equilibrium line. This is the point at which the glacier transitions from the climatic regime where there's more snowfall than snow loss to the climatic regime where there's more snow loss than snowfall. So this is why it's really critical that a glacier spans a range of climate regimes. If, for example, this glacier just lived in an environment where snow falls and sticks around, then that glacier would build up and up and up and up infinitely. But because ice flows under its own weight, as it builds up, it will flow away from that climate regime. And it will flow into an area where that net accumulation isn't positive. So ultimately, this system maintains balance because ice flows from the accumulation zone into the ablation zone. And so even though there's extra ice added in the accumulation zone, some every year flows into the ablation zone where it's lost. So this whole system maintains this kind of dynamic equilibrium where year over year, the total ice of a healthy glacier system may not change, even though in some areas it's melting, in some areas it's being added. One thing that's true about every glacier system is that they form from meteoric ice. Meteoric just means it falls from the sky. That means snow. So glaciers are fundamentally formed by snow that's buried and densified through time. When we describe the materials that make up a glacier, we can use a couple of different terms. Up in the near surface, we have snow, which tends to be relatively low density because it's this mixture of ice and air. if you were to go shovel a bit of snow off the ground after a snowstorm, you would see that between each of those individual snow crystals, there's a little air. There's air that's kind of porous and permeable running through the whole medium. And snow typically has densities from, I don't know, about 250 kilograms per cubic meter up to 550 kilograms per cubic meter. As that snow is buried, those crystals start to change. They metamorphose slowly into an intermediate product that we call firn, F-I-R-N. And the process of that transition from snow to firn is actually one that's of great interest to people who study glaciers. Eventually, as the snow continues to get denser and denser and denser into firn, as the firn gets denser and denser and denser, eventually that air that's between the ice crystals transitions from this porous, permeable pore space into closed-off bubbles. Eventually, after we close off bubbles, we end up with what is primarily continuous ice crystals with these separate pockets of air, and that's what we call glacial ice. Glacial ice has a density of about 917 kilograms per cubic meter. So when we're thinking about the material that makes up a glacier system, we have snow, we have firn, we have ice. And in that ice, there's trapped gases in bubbles, which becomes important when we think about ice as a climate proxy, as a proxy for past climate change. Because ice flows under its own weight, in some areas at high latitudes, that ice flows out toward the ocean. And so one thing that's important to keep in mind is this idea of flotation. Ice is a really unique Earth material. It's one of the few materials whose solid phase is less dense than its liquid phase, which means that ice floats on water. If we imagine we have some ocean system, I'm just going to draw a hypothetical for a moment. Here's the seafloor over here. Here's the ocean surface. And let's imagine I dropped an ice cube in that ocean. You often hear the trope that 90% of an iceberg is below the water level. That's because the density of water and the density of ice are about a factor of 0.9 to 1. So we would expect that that ice cube has to displace the exact same mass of water as is contained as H2O molecules in that ice. So if we were to add ice to the top, add ice to the top, add ice to the top, the surface would move up, but it would move up slower than the bottom would move down, because that iceberg would sink down as we add weight to the system. Eventually, if you kept adding enough ice to this glacier, I didn't really draw this to scale, but that's okay. Eventually, it would get so thick that it would rest on the seafloor. If you were to continue to add ice to this system, it couldn't sink anymore, right? Because it's sitting on the seafloor, and so it would just build up. This ice down here, the exact thickness of ice required to sit the ice on the ground, if you melted all of that ice, sea level wouldn't change at all, because that's the exact amount of water that you would add to the ocean to fill back in the space that's currently occupied by ice. But melting this stuff up here, that does contribute to sea level, and it's an important component of the glacier system that we call ice above flotation. Something to keep in mind. But the reason I talked about this wasn't to go into the details of ice above flotation. It's to help you think about the fact that some glaciers flow out over the ocean and eventually thin to the point where they're floating on ocean water. So that gives us a few additional terms that we have to think about. This ice sheet, this cross-section of an ice sheet we have on the left, is a nice little cartoon that illustrates, for example, what the West Antarctic ice sheet looks like. It's sitting in an ocean basin. In many places, it's thick enough that it's sitting on the seafloor. But as it gets out towards its edges, the ice tends to get thinner, and eventually it's thin enough that it goes afloat. This transition point, where we go from ice that's sitting on the seafloor to ice that's floating, we call the grounding line, or kind of in more modern nomenclature, the grounding zone, because it's not a perfect line. Upstream of the grounding line, in this case, we have an ice sheet. This is just another word for glaciers that sit kind of at continental scale. And as we talked about before, some of that ice sheet ice sits what we call below flotation. This is just the amount of ice we need to get that ice sheet to rest on the seafloor. And some of it is ice above flotation. The ice that has a potential to contribute to sea level rise. This floating extension of the ice sheet that sits all the way out here, we call that thing an ice shelf. Importantly, ice shelves are still glacial ice. They originated as snow that was buried and becomes densified as snow is buried and metamorphoses under its own weight. This is different from something that you may have heard about called sea ice. Sea ice is also ice that floats out on the ocean, but sea ice forms by the direct freezing of seawater. Sea ice tends to be a few meters thick, ice shelves tend to be hundreds of meters thick. So they're quite different systems. Then you can see out here, we have drawn a term that's probably quite familiar to you, iceberg. Icebergs are former components of a glacier system that have calved off, that have separated from the glacier. Once they've calved off and they're floating away, they've already done their contribution to sea level rise. They go out into the ocean to melt. So over here on the right, we have a drawing of Greenland up here, one of Earth's major ice sheets, and Antarctica here. Around them is sea ice, some of that ice that's frozen directly out of ocean water. But if we look at the Antarctic ice sheet has three major ice shelves, kind of country-sized floating extensions of the glacier itself. There's the Ross ice shelf here, the Filchner-Ronne ice shelf here, and the Amory ice shelf here. So hopefully this gives you some of the kind of vocabulary that you'll encounter when you're reading literature about ice sheets and glacier systems. You can always come back and review this later if you're confused about any of the relevant terms.